Smoothing spline is a non-parametric method and very related to cubic spline method, natural cubic spline method, which basically find function f hat that minimize the RSS value. So yi minus f hat xi square plus some additional cost function for your regularization purpose. F hat second derivative t square dt. Okay, here f hat can be anything that can define second derivative for all range. Okay, so f is any function has the second derivative function. Okay, so here f hat has an infinite degree of freedom if we don't have this part. If we don't have this part, f hat has infinite degree of freedom, and we can always make RSS value equal to 0. But this additional cost function is regularizer. We can control some degree of freedom virtually, and actually we can control the overfitting issue using this additional cost function. Ritchie regression, Lasso regression, they all include this kind of additional cost function. One is L2 regularizer and L1 regularizer, so that your output becomes more smooth or more general, so you have less overfitting generalization gap. Okay, so the definition of smoothing spline also incorporate with this additional cost function, and this additional cost function defined with second derivative square, so that your f hat becomes more smooth over whole range. And very interestingly, a natural cubic spline with not boundaries at every training data point is the solution. So f hat always is a natural cubic spline with not at x1 through xn. Okay, so why? When you have this not, then natural cubic spline, what is the degree of freedom of the natural cubic spline? It's n. Natural cubic spline have the same degree of freedom with the degree of freedom of natural cubic spline is the number of knots. And here we have n knots. So degree of freedom in this case is n, the number of data point. When you have the same degree of freedom with the number of your training data point, which basically implies that you can perfectly fit any input-output pair. So for any x1, z1, x2, z2, up to xn, zn, you can define a natural cubic spline G such that Gxi is equal to Zi for all I. So here G is a natural cubic spline. Okay, and we can uniquely define a natural cubic spline for a given set of pairs. Okay. And let's imagine there is some another function G tilde that also has Gxi equal to Zi for I, but this is not natural cubic spline. Okay, and let's say Hx is equal to G tilde x minus Gx. So now I will show that G tilde second derivative square dx greater than or equal to G to prime x squared x. Then from this property, we can always say this. For given f hat xi target output, you can minimize this additional cost part only with a natural cubic spline. So which means if you use some other function, not a natural cubic spline, you can find a corresponding natural cubic spline that share the same output for every knot x1 through xn, but can decrease this additional cost part. So which means there's no reason you pick function that is not natural cubic spline. Okay, so this is enough to show the solution of smoothing spline is a natural cubic spline. Okay, how can you show this? G tilde to prime x squared dx, this is equal to G to prime x plus h to prime x squared dx from the definition of hx. This is equal to G to prime x squared dx plus 2 times G to prime x h to prime x dx plus h to prime x squared dx. And we know that this is always non-negative because this is integral over some square function, non-negative function. So once we show this is equal to 0, naturally we can conclude the integral g tilde second derivative square is greater than or equal to g second derivative x squared dx. Okay, so this is sufficient condition of what we want. So we have to show this. Then what is g to prime x h to prime x dx? From the definition of natural cubic spline, and we know G is a natural cubic spline. G to prime always equal to 0. The second derivative of G is always equal to 0 at the first interval and at the last interval. So this is x1 through xn. G to prime x h to prime x dx. Okay, and this is equal to g to prime x h prime x x n x1. You know this property, right? G is 3 prime x h prime x dx. And again, we know that g2 prime x at x1 and g2 prime at xn is equal to 0, because the natural cubic spline has to have linear function at the beginning and at the last. So this is 0. How about this part? We know that the g3 prime x, the third derivative of your natural cubic spline, is piecewise constant. This is piecewise constant. So this is equal to sum of I1 to n, right? Some constants, so I2 to n. Okay, some constants I times integral x I minus 1 x I h prime x dx. And from the definition of h function and from the definition of g tilde function, the g tilde function and g function have to share the same function value at each node. So we know hxi always equal to 0, which means this value always equal to 0. So this is also 0. So we have this part equal to 0. That's it. We just finished the proof. The solution of smoothing spline is a natural cubic spline with nodes at x1, x2 up to xn. Okay, good, great. So from this property, we can derive a smoothing spline. F hat x is equal to beta 1 and 1 x plus such that n1x is equal to 1 and 2x is equal to x, n2 plus k x is equal to d kx minus d n minus 1x and d kx is equal to x minus xk plus cube minus x minus xn cube xn minus xk. Okay, from this, when we define matrix n as n1 x1, n2 x1, n x1, n1 xn, n xn, beta vector is equal to beta 1 to beta n, y vector equal to y1 through yn, omega matrix is equal to integral n1 to prime x n1 to prime x dx, n1 to prime x, and n to prime x dx, and n to prime x, and 1 to prime x dx, and n to prime x, and n to prime x dx. Then we can have this closed form equation for your parameter beta. This is equal to n transpose n plus lambda omega inverse n transpose y. So this is the solution of smoothing spline. And y hat is equal to, from this, s lambda y, here s lambda is equal to n transpose n plus lambda omega inverse n. Okay. So here, one very interesting remark here is essentially the trace of S lambda matrix indicating some virtual degree of freedom. So this go to 2 as lambda go to infinity. Essentially, when lambda go to infinity, your solution becomes a linear function. And this go to n as lambda go to 0, which is basically interpolating every your training data point.